Right, I'm going to go with a sine one as well. So remembering from the top of the page, we said that if we're looking for a sine, it's the imaginary part of the expansion. So we're going to expand the complex number into something like this using the binomial theorem, and then this time we're going to be interested in the imaginary portion only. Okay, so let's have a go at doing this. So what we're going to say is that sine 5 theta is going to be the imaginary part of cos theta plus j sine theta to the power of 5. So we're just going to be worried about the imaginary portion of it. Okay, so the first thing we've got to do is we've got to do this expansion, which is cos 5 theta plus 5 cos 4 theta j sine theta plus 10 cos cube theta j squared sine squared theta plus another 10 cos squared j cubed plus 5 cos theta j4. We're going to have room here, swizzle along, plus j5 sine 5 theta. I used a square bracket, so I might as well go back to a square bracket. Okay, so this is the expansion of that, once again using the binomial theorem. The coefficients for the binomial theorem come from Pascal's triangle. So 1, 2, so adding up. So 1 and 2 is 3. So there's the 1, 3, 1 that I used previously up here. 1, 3, 3, 1. And if we carry on with the triangle, we get 4, 6, 4, 1, 5, 10, 10, 5, 1. So that's where that 1, 5, 10, 10, 5, 1 comes from. Okay, now I'm only interested in the imaginary portion of this, so I'm going to cross out anything which is a real number. So that's a real number. This one's imaginary because it's got a j. J squared is -1, so that goes back to being real. J cubed is imaginary. J to the power of 4 is real, and j to the power of 5 is imaginary. Okay, so now I'm just going to work out what these things are. So this has got basically want a j out the front of it. We've got 5 cos 4 theta sine theta. If I take one j out of the front of that, I'm left with j squared, which is negative. So it's going to be minus 10 cos squared theta sine cube theta. And I take one j out of the front of that, I'm left with j to the power of 4, which is j squared squared. And j squared is -1. -1 squared is 1, so it comes back to being positive again. So plus sine 5 theta. Okay, and like I did right at the top, it's just the piece without the j that I'm interested in. So it's just the piece inside my large square brackets. So you could have thought about saying, if you want that, this might be handy notation. So all we're saying is that sine 5 theta is equal to 5 cos 4 theta sine theta minus 10 cos squared theta sine cube theta plus sine 5 theta. Okay, so now I have it in terms of some sines and some cosines, and if I want it just in terms of sine, I need to use the same substitution I made previously. So I need to use the substitution that cos squared theta is 1 minus sine squared theta, and I need to replace all of my cos squared thetas with this, expand the brackets and carry on. And if I do that, which I'm not going to do, but if you go away and do it yourself, you'll find that you come up with 6 sine to the power of 5 theta plus 10 sine to the power of 4 theta minus 10 sine cubed theta minus 10 sine squared theta plus 5 sine theta. Assuming I didn't make any mistakes the first time I did it. Okay, so again, it's just a really useful tool for being able to take the sines of compound angles and expand them all out and get them in terms of just a single angle. And that, I think, is the end of complex numbers.